What are we going to do today? We're going to use substitution to invert the chain rule. We're going to identify a u. We're going to manipulate that function so that we change all the variables around to make it easier to integrate. The whole point of this is that we're going to be getting ones where, all the things that we've learned how to do so far, we can't do them. So we've got to change stuff around to make it so we can do them. And it really does help to understand that this is basically just taking the chain rule and doing it in reverse. So like here, I've got two different things that we don't know how to deal with. Like I never went over the thing that you take the derivative of and you get the tangent function, or the thing you take the derivative of and you get the cotangent function. So what I want to do is I want to take a second and I want to explain how use substitution works. The idea is we've got something we can't use and we want to take it and turn it into something that we can use. So for example, for the tangent function, in order to deal with it, we have to break it down into sine and cosine, right? So what we want to do is we want to pick one of those things that's going to be our u and another thing that's going to be our du, so that we can basically rewrite it in terms of u and du instead of the function and dx, and then have it be something that we now know how to integrate. So I'm going to do these with little explanation just because I want you to see the process, and then we're going to go through and we're going to identify, and a lot of this basically boils down to, can you see the pattern? Can you make it fit? So if I choose cosine as my u, then I can get like a 1 over u type situation, which we know how to do that. The integral of that's natural log. So if I make u equal to cosine of x, then I can take the derivative of both of these, because I've got a dx here too, right? I don't have any kind of dx, so I've got to make a dx as well. So I'll take the derivative of both sides. The derivative of cosine is, in fact, negative sine. And what I want to point out here, just before I do my thing, is that, look, in taking this u and taking the derivative, I generated all the rest of the stuff that I'm missing. So I don't have a negative in here, so I'm going to take this negative and I'm going to flip it over to the other side. So what I can do is I can say, all right, well, sine of x dx, that can be my negative du. Cosine of x, that can be my u. And I turn this into the integral of du over u, which I know how to integrate, right? Or a negative du over u, because that's negative here. But the negative. So this becomes negative natural log of u. And now, to finish up the problem, plus c. To finish up the problem, I can put this function back in for u to get it back in where it needs to be. And so I've taken the integral of tangent of x dx. I've rewritten it into something that I can actually take the derivative of, take the integral of, and then I integrate it, and then I put the x term back in so that I can finish my problem. And then I have seen some people be like, well, let's take this negative, bring it up into the exponent, and turn this into natural log of secant x, but forget that. This is fine. So we've got the negative natural log of cosine of x plus c. That is what the integral is. Let's do the same thing with this one. First of all, this is cotangent, right? So let's write this as cosine over sine. So I'm going to do the exact same thing. This time, my u is going to be sine x, though. My du, therefore, is going to be cosine x dx. So I've got all my things accounted for. I'm going to replace, right, cosine x dx. I put du in its place. Sine x, I put u in its place. Well, this is just natural log of u plus c. Then I'm just going to plug it back in. What was u? Sine of x. I chose these specifically because I think we've spent a lot of time defining the integrals of trig functions and the derivatives of trig functions, and I think it's important that we can do it with everything when possible. All right, let's do a whole bunch of examples. We'll do this with indefinite integrals with the plus c stuff, and then we'll also do it with definite integrals where we have the top and bottom limits, and we'll talk about how to work with those as well. So here's our first example. I want to take this and I want to integrate it. Now you could do this without any kind of fancy tricks like we're trying to do today. If you wrote that out as 2x plus 8 times 2x plus 8 times 2x plus 8 and foiled all that together and got your thing and distributed it in the 2 and turned it into one big algebraic expression, you could have your answer and be done. But who wants to do that? Nobody. That's a lot of work. Here, I'm going to show you an easier way. The whole problem is that I don't know how to integrate this the way it is, but if I simplify this, if I take this thing here in the parentheses, and I turn that into u, I'm going to be able to simplify this down. So let's say u is 2x plus 8. And now let's calculate our du. The derivative of 2x is 2. The derivative of 8 is 0. And don't forget your dx. So now look what I have. Here's 2 dx right here. I don't have to do anything extra, nothing special. So let me take all these things and cache them in. U cubed, and then this 2 dx turns into our du. Look how much easier this is to integrate than this. Well, let me do that. U to the 4th over 4 plus c. And now all I have to do is, well, what's u? It's 2x plus 8. So let me just do that. Bring it back to where it was. And that is my final answer. So once again, let's talk through this process. Step 1, identify what u is going to be. It's usually going to be something inside something else. Make our lives easier. Second, take the derivative, get your du, and then integrate your much easier problem once you plug everything in that needs to go. So let's take a look at this one. Same idea. I look at this, and and you can think about it in advance. X squared plus 6, if that's my u, my du is going to be 2x. Oh, look, there's a 2x out here. Hey, I must be on the right track. Right? Well, look, I've got all my things. 2x dx x squared plus 6. That's all. So let me integrate now. Let me put it, you've got u to the negative 3, and then du. Oh, let me integrate that. Raise that up by 1. And then plug everything in. Ta-da! All done. Again, once you see the patterns, it's going to be super duper easy to do. It's just a matter of looking for the patterns, paying attention, and not thinking too hard. If you overthink it, it's going to be a problem. If you don't overthink it, it's going to be easier. Except this one. This one is hilarious because you can make this as ridiculous as you want to, right? Like I can actually, what makes this really ridiculous is that I can actually do like a u sub within a u sub. I can be like, all right, well, let me call this u. Well, then my du is just going to be 1 dx. So let's look at what this is. But you go through and you can probably just do it with this. Actually, you know what? Let's just, I'm trying to overthink this, I think. So let's call this a different letter. Let's call this W. So then DW. And then and then chain rule. There we go. There was like a really cool trig identity that you could use to make all this simpler looking, but this is just as easy. Because look, I've got the sine u, cosine u, du right here, and then just like an extra 2. So here's this, here's this. Let's get everything to the other side just to get. So then I can take this and I can replace it with half dw. So look what I have left. W. And then I can take this half and put it outside. Right? So now let's integrate this. This is w to the 1/2. So let's make this w to the 3/2 divided by 3/2 plus c. And let's simplify this, because when you divide by 3/2, you're dividing by 3, multiplying by 2. So that's going to cancel out with this 1/2. We'll have 1/3 w to the 3/2 plus c. And now we can replace w and u, right? We can turn this into 1/3 1 plus sine squared u to the 3/2 plus c. And now we can go back one more. U is x minus 1. Sine squared of x minus 1 to the 3/2 plus c. So again, this is like the most ridiculous one I've ever done. You're not going to have many that are going to come out like this. I guarantee you on the AP exam, they're not going to throw something like this at you, because you're going to be looking at problems that you can do in under a minute for sure. I mean, this is a really complex one, but you can do it. That's what U substitution does for you. It allows you to go from this ridiculous thing and break it all the way down to this thing that you can actually do yourself. All right? let's move forward. There we go. So again, it helps to take a second and look at what we have. Here on the inside, we've got a 5t squared. Here on the outside, we've got a t. So automatically you should be thinking, all right, well, wait a minute, hold on. That works. I also want to point out you have this. This tells us that we'll be able to actually find C. And we can have a calibrated solution. I call it calibrated. I think they'll call it like a particular solution. Like there's a general solution where it's something plus C, and then there's a particular solution, which is where you find what C is, and you get everything in terms of the function that they actually want. But what you're doing is you're calibrating your answer. I like to use the word calibrate because I think it really drives home what we're trying to do. So let's do it now. So here's our u. Again, it's on the inside of a function, so it's probably what we need. So we're going to say, all right, well, u is 5t squared minus 3. So let's take the derivative. du is just 10t dt. So now here's the thing, though. Look, see, this is 20. This is 10. So in order to have what I want on the inside here, I've got to multiply both sides by 2 so that everything matches. That's a 20, needs to be right. So what they would say is, hey, bring this up here, and you can integrate, and you'll end up with u is this thing, du is this thing. This is really just u cubed du, and then this extra 2 goes out here. So let's do it now. U cubed gets integrated to u to the 4th over 4. That 2 and that 4 are gonna cancel out. Let's take care of that. So here we have our general solution, but now they tell us, hey, s of 1 is 15. That means when t is 1, s is 15. So let's find c. Well, let's plug back in what we've got for u, right? So let's do that. U is 5t squared minus 3. And then we're going to say when t is 1, s is 15. So here we're going to plug in 15 for s. We're going to plug in 1 for t. Be a 4. I don't know what I'm doing here. U to the 4th. I think I got confused by that square. Anyway, so let's do what's in here. 1 squared is 1. 5 minus 3, so that's 2 to the 4th plus c. Well, what's 2 to the 4th? 2, 4, 8, 16, right? So 15 equals 8 plus c. Well, what does c have to be? What's 15 minus 8? Well, that's c. So we found c. So here's our general solution. That's our general solution. Now let's write our particular solution. Do, do, do. Five t squared minus 3 to the fourth plus c, which is 7. So this right here is our completed problem. So once again, with the information that we're given, we did our use substitution, found the general solution, then we calibrated it, found C to get our particular solution. All right, let's continue. Let's do a bunch more of these. Once again, they're going to tell us information for us to calibrate. So let's calibrate. Right, this is our function right here. What we want is to integrate this. So let's do that. Bloop. So we got to take our u here, right? So we've got equals all over the place today. I'm sorry. T plus pi over 12. So du is same as dt. So now we've got ds, ds over du, 8 times sine squared of u. Okay, so how do we deal with this? How do we deal with sine squared? Well, sine squared, where is that trig identity? 1 minus cosine squared, yeah, but there's like a way to get it to... Oh, yeah, okay, yeah. So, oops, cosine of 2 theta is 1 minus 2 sine squared theta. So let's solve for sine squared theta so that we can get what we need. Subtract 1, divide by negative 2. And so what we're going to be able to do here is we actually have exactly what we need now. I'm going to neaten this up, and then this is times 8, right? So minus 4 cosine of 2 theta. Well, 2, what did I have? U, right? Minus 1. Minus 1 times 4 is 4. Okay, but now we can integrate this. I know how to do this. Du, du. Because remember, when I integrate like cosine of 2u, it's like 1/2, right? Dividing by that 2, just like if we were going the other way, we'd multiply. So what do we have? Negative 4 times 1/2 sine minus, that was a 4, plus c. And then let's make this all nice and neat. -2 sine of 2u minus 4u plus c. And then we can bring it back. We can go back all the way to this. Do we? Why? Why do we have to do that? We don't. If I plug in 0, I get 5, right? If I plug in 0, I get 5. Well, if I plug in t as 0, I get 5. Yeah, okay. So let's go back. So 2 plus 2 times, so pi over 6, right? Minus 4t plus pi over 3 plus c. So now if I plug in 0 for u, I should get 5. Zero plus pi over 3 plus c. All right, so what's sine of pi over 6? 1/2, right? So this is -1, so we get 6 minus pi over 3 equals c. And so our final official complete solution, once we clean this up, plus pi over 3 plus 6 minus pi over 3. And look, the pi over 3's actually cancel. So let's, so this right here is our complete, calibrated, full solution. And again, some of these are a bit wacky, and that's okay. It's okay that some of these are a bit wacky. Once we get used to doing it, these will feel super easy. All right, let's continue on. Again, if you look here, you got this on the inside, this on the outside. That's a clue. That's a hint, right? Make this your u. And make this your du. Right? If I take the derivative of t to the fourth, I get 4t cubed. If I take the derivative of 5t, I get 5. And you're not actually thinking about what this is going to be. You're just taking the derivative of both sides to get your du. And then this right here, isn't this what this is? These are the same. That's what we want to be true. That's what we want to happen to make life easy. Because now we can take the integral of square root of u du, because here's this 4t cubed plus 5 dt, that's just du. So we collapsed all of that Now, what I'm sick of doing is I'm sick of trying to figure out, like, going all the way back, and then I'm gonna have to evaluate, plug it in, and do all that stuff. Who wants to do that? Nobody. So here's what we can do. We can change these limits, because these are in terms of t, right? T equals 0 to t equals 1. Well, if t is 0, what's u at that spot? What's 0 to the 4th plus 5 times 0? And that's still 0. What about 1? What's 1 to the 4th plus 5 times 1? 1 plus 5 is 6. So what I did is I changed these limits so that I don't have to worry about t anymore. T is now gone. It is removed from history. Nobody cares that t ever existed. I can just continue on with this easy problem instead of going back and trying to do that ugly godforsaken thing like I did last time. So let me integrate. Remember, this is u to the 1/2. So we've got the integral. So I'm going to do u to the 3/2 divided by 3/2. And now I don't need the plus c because this is a definite integral. I'm going from 0 to 6. Right? So let's simplify all this first. So I need to take the top one, plug it in, and then subtract the bottom one when I plug it in, right? So I've got 2/3 of 6 to the 3/2 minus 2/3 of 0 to the 3/2. Well, 0 is going to make this not a going concern, right? So let's see if we can simplify this. Well, to the 3/2, right? That's the same thing as 6 cubed and then take the square root. One thing you can do is think about it like, so you can think about it like, well, 6 to the 1 and 6 to the 1/2, right? And then the 1/2 is just radical. And then you can cancel. 6 divided by 3 is 2. So this actually simplifies very nicely into 4 radical 6. But like on the AP exam, they're looking for a number. This is a number. You can leave it here instead of going all the way down to this. Remember, you can make your graders work for their money. Don't be afraid to make your graders work for their money. All right, let's try another one. Same idea. So look, I've got this situation, right? The cosine is to the -4th. That's the one I'm going to want to make my u. I'm going to want to make u equal to cosine of 2x. That way I can have u to the -4th. Something. Now let's take the derivative. So it's a 2x, so I got to have -2 sine of 2x dx. So you'll notice, what do I have extra? I've got this extra -2. I've got to deal with that. So let me move this -2 over to the other side. And look, now this is the same as this, and I can just take this and plug it in for that. So what do I actually have? I've got u to the -4th du, and then this -1/2 comes to the outside. Well, hold on, the limits. I got to take care of those. Well, if u, whatever this is, I've got to find out where x is 0. Well, cosine of 0. Right, 2 times 0 is 0. So what's the cosine of 0? Cosine of 0 is 1, isn't it? Pi over 6. I want the cosine at 2 times pi over 6, which is pi over 3. Well, isn't that 1/2? So that's what we're going to do. Now we're going to take the integral just like we're used to. But now I don't have to worry about x anymore. I don't have to worry about sines and cosines anymore. I can just do the integral of u to the negative fourth. That's so much better. And I'm going to do that. I'm going to go from 1 to 1/2. Now, if that looks silly, it's like, oh, I'm going from a bigger number to a smaller number. Remember, you're allowed to flip the limits if you change a sign. So if you throw yet another negative sign onto that pile, you can switch the limits. But it doesn't matter. You will get the exact same answer regardless. So let's make this nice and neat first. The negative 1/2 and the negative 1/3 conspire to make a 1/6. U to negative 3 from 1 to 1/2. So now let's take care of this. I'm going to plug in 1/2. And u to the negative third is 1 over u cubed, right? So 1 over 1/2 cubed minus. And we'll clean this up. This is kind of a hot mess right now. 1 over 1 cubed, right? So 1 cubed is 1. So this part is 1/6. That's great. 1/2, if I did 1/2 cubed, I get 1/8, but it's in the denominator, so I can make just 8, right? 1 over 1 over 2 is just 2. So 1 over 1 over 8 is just 8. So we got 8 over 6 minus 1 over 6. So that's 7 over 6. All right, a couple more. Again, we've got a definite integral, which means that we can, once we figure everything out, we can say goodbye to all that extra garbage. We don't care about that sine and that cosine. Once we figure out what our u is, and our u probably should be this thing, right? Well, so that means our du is 2 sine t, right? Because derivative of cosine is negative sine. It's going to cancel out with that negative sign. dt. Well, hey, sine t dt, sine t dt. The only thing I'm missing here is that 2. Let me. And then you've got a 3 out here. You can also bring this 3 out. So what's going to end up happening, we brought the 3 out, we brought the 1/2 out. This is going to be a 3 over 2 out here, right? And then now this is our u. And then our du. So let's do it. Let's take care of this. So we integrate. Well, what are our limits? 0. Well, if x is 0, or t is 0, cosine is 0. Cosine of 0 is 1. So this is 5 minus 2, which is 3. And then at pi, cosine is negative 1, right? So that'll be 5 plus 2, 7. See, again, much easier now. I don't have to deal with ugliness. Can you imagine if you had to actually do that out on its own? No, because most of us can't. So we're going to integrate. This is u to the 3 over 2 divided by 3 over 2. And if you notice 3 over 2 and then a 3 over 2 in the denominator are going to cancel out, right? Because it's secretly 2/3, and 3 over 2 times 2/3 is 1, right? We're going from 3 to 7. So these cancel out. We're left with u like that minus like that. And as far as I'm concerned, you can just leave it here because it doesn't get any better. Even if you were to break it down into like radical like things, you can't do anything with that anyway. You might as well just leave it right here. Again, make your grader work for their money. Don't let them off the hook. Otherwise, it's a free vacation for them. Make them work. Ooh, I love this one. The reason I love this one so much is because this one, until you see it, looks completely whacked out. It looks completely weird until you realize that u is going to be this. Why? Well, let's take a second. Remember, the derivative is 1 over u du, right? 1 over this thing times the derivative. So 4 over 4x minus 5. Look, 4 over 4x minus 5. So the thing of it is, experiment. Look around, because you're going to find the answers in the most unlikely of places sometimes. So we got the u here. That's in the denominator. So this is 1 over u. And then du. And what's the integral of that? Well, we don't have any kind of, so we're stuck going back to dx. So this is going to look hilarious. I love it. The natural log of 4x minus 5 plus c. So some of you may be looking at that going, but Mr. Webster, there's absolute values on the outer ones and just normal parentheses on the inner ones. What's happening? Well, the thing of it is, when you integrate from something else to a natural log, remember that natural log has a domain from 0 to infinity, not including 0, right? All those negative numbers are not okay. But the function we started off before then was this, right? When you have a function that starts out with something other than that, 1 over x has negative answers that work, but natural log doesn't. So when we go from something that does have negative numbers to something that can't have negative numbers, we have to find a way to restrict the domain. And so this outer one came from something that had negatives and now it doesn't. This inner one started out its life as a natural log. It was never going to have any of that. So we can leave those with parentheses. If you're remember back in like algebra 1 or middle school, whenever you learned how to take the square root of something and you went, okay, well, if I take the square root of 4, it's plus or minus 2, right? But if the square root was already there, I don't have to worry about it. I just do what's there. Same thing here. If I create a natural log, then the absolute values have to come on. If the natural log was already there and there's parentheses, you can leave those with parentheses. But either way, this is your answer. All right, last one. Again, same issue, same problem. It's like, okay, well, how do I deal with this? Make your u the natural log of this. Well, how's that going to help? Well, first of all, right? And then you can bring this down to make life easier on yourself. So if my u is natural log of 11x, my du 1 over 11x times the derivative of 11x, which is 11. Well, that just simplifies. Then don't forget your dx. Well, look here, 1 over x, that's the missing part, right? 1 over x dx, that's what this is down here. So we've got, let me rewrite this. This is this over that. And what this becomes, and we can take that 1/2 and bring it outside. Again, u is this, du is this. So much easier now. Why is it so much easier when we do this? Because it's a special trick that allows us to do this very easily. So we've got 1/4 u squared plus c, and now we got to go back in. U is natural log of 11x, so 1/4 times the natural log of 11x squared plus c. Now this isn't the natural log of 11x to the second power. This is, we're squaring that whole function. So just be aware of that. That is a different thing all entirely.